welcome back. And today we're going to talk about heat. Heat, of course, as a form of energy. Heat energy. First, we'll describe what heat is. Heat is it's basically a description of the state of the molecules inside some kind of substance. So heat can be expressed as a couple of things. There's two major ways we can describe heat. One is it's a form of kinetic energy. That's energy because something is moving. And it's the actual molecules, kinetic energy of the molecules. And basically speaking, the faster the molecules move, faster they move, the hotter they are, the more heat they have, or the more heat energy. So, simply put, if we imagine, some object, here, big bar of metal, and we light a little fire under here to make it hotter, there, we'll put a little flame, there we go. What happens is the molecules inside here, as the heat energy strikes the molecules, it causes them to vibrate or shake, right? They vibrate and shake back and forth. They jiggle, each one. And so the more they jiggle around, the hotter the substance becomes. So this is a kind of kinetic energy. It's movement of the molecules. And this is how we describe heat in matter, anything that's made of matter. This is how we describe it. What's interesting is the particles are always jiggling a little bit, even when it's really, really cold. When we measure heat with temperature, we use the Celsius scale quite often, or sometimes the Fahrenheit scale, but these scales are just scales that were developed for our convenient use in our everyday lives. So when we talk about 0 degrees Celsius, right, which is the freezing point, that's pretty cold. But we know we can go below that. We can go to -10 on a very crisp winter day, or even as cold as -30 or 40 degrees Celsius. But it doesn't get much colder than that for most of us. Most people live in places in the world where those are the most extreme temperatures. But it is possible to get colder. And of course, we also know that on a warm summer day, we can get as high as 30 degrees Celsius. And water boils way up at 100 degrees Celsius. But again, in our everyday lives, we don't go much beyond this range. And that's why the Celsius scale is useful for us. But for scientists who need to be able to go much hotter and much colder, this isn't always the best way to do it. So you'd think that 0 is kind of where the particles would have no heat, but that's not true because we can get colder and colder as we go down. So there's another scale of temperature that is basically sets 0 at the bottom where there is no heat, which means there is no motion of the molecules at all. Even at -40, molecules are still jiggling a little bit. They're jiggling around. At 30 degrees, they're jiggling a lot more, right? But the jiggling gets smaller and smaller until we get down to this. And this is, of course, 0, and the unit is the Kelvin. Let me just erase what I wrote there. Oops. Let me erase this part for a second. And this new measure is called kelvins. It's a metric measure, kelvins, like meters or grams or anything like that, kelvins. And we don't use a degree sign when we use kelvins because it's a metric unit. So we don't use the little 0. We don't say 0 degrees Kelvin. We say 0 kelvins. That means that there is no vibration at all. As far as we can tell, this is impossible to actually achieve. We can suck the heat out of things and make them as cold as possible, but we can only get to a temperature very, very close to 0 kelvins. We can't actually make everything stop. There's something interesting and unique about particles. They always have to be moving, even a tiny little bit. But the jiggling in near 0 kelvins would be almost nothing. So if we go up the Kelvin scale, we get up to 273 kelvins. That's the same as 0 degrees Celsius. So when we go outside and we say water's freezing at 0 degrees Celsius, we measure that as 273 kelvins. So you can see how there's a long way to go to get cooler. All right, so it's the jiggling of molecules, and it's a pretty straightforward concept. The molecules jiggle, and or particles of any kind. Molecules, they could be ions, they could be even elementary particles in something that's very, very hot. And of course, what happens is if you heat molecules and things too much, they jiggle so much that they begin to fall apart. And that's why things sort of change their state, and things change their obvious appearance to us. The more they jiggle, the more they're sort of disrupted. They start to change their molecular interactions. Things melt, right? And then they turn to gases. And then even gases, if you heat them enough, the actual molecules can fall apart into ions and elementary particles and things. And we get very hot mixtures of vibrating particles. Okay, so that's one way that heat can be described. But there's another way that heat can be described that has nothing to do with matter at all. What we've realized since the early 20th century is that there is this thing. There is this thing called the electromagnetic field. Now that's a big word, but what it means is it's kind of like, imagine if you were a fish, okay? So here's the ocean, right? And you're a fish living in the ocean. All around you is ocean. And to be honest, if you were a fish and you lived your whole life in the ocean, you probably wouldn't even really be much aware of the ocean. Kind of like us, we very seldom think of the air. We're living in air all the time, and we never really think of it. But the fish is also living sort of in the ocean. Now, what's interesting about this is the ocean itself can wiggle and move, and there can be waves, right? Waves and currents and jiggling of the ocean. And these little waves and currents can actually affect everything that floats in the ocean. They can make these things jiggle around. So there is this thing called the electromagnetic field, which is kind of like an invisible ocean that surrounds us. We can't actually see it, but it's there. And guess what? Just like an ocean, it can have waves in it, and these waves can actually affect things in our world, and we can notice these effects. It's like an invisible ocean. Now, it's not an ocean of water, okay? You could think of it as a substance that affects charged particles. The only thing that this ocean will bump and jiggle around are particles that have charges. And so primarily for what we're talking about, electrons and protons. And I would say that most of the things that we notice, electrons, are from electrons being jiggled about. But any charged particle could work. Theoretically, if you were to rub a balloon on your head and you became charged, then there could be an effect on you from this ocean that's wiggling all around you. Okay, so let me just quickly explain how it works. Let's say you have a particle. Let's use an electron. It's a good example. An electron has a negative charge. So if you were to take an electron and you were to poke it with your finger, bonk, like that, then what it would do is it would sort of wiggle. You would jiggle it, right? And as it jiggled, just like if you just think about a cork floating in very calm water, right? And we'll draw this view, and here's the view of the cork from the top. If you push on the cork will bob up and down. It'll start to go up and down. And what it'll do is it'll make little ripples in the water that will go out. And you would see that sort of as rings of waves coming out from the top view, right? These are things, and they would move outward in all directions like this. So when you jiggle a cork in still water, it makes ripply waves in the water. By the same sort of analogy, if you poke or wiggle or do anything that disturbs charged particles, they will make very similar ripples and waves in the electromagnetic field all around us. So this electron will begin to make waves, and these waves will go out in all directions. And they'll also go in and out of the board. They're three-dimensional waves. They come out, they go out from everywhere. And these are called electromagnetic waves. And you can kind of see the word in here, electromagnetic. The electro is referring to the charge, the plus or the minus charge. Magnetic is in there because we realize that magnetism is also very closely related to charge. And so the two are kind of go together. So electromagnetic waves are waves in the electromagnetic field. And those waves come in all shapes and sizes. They can have very small bumps that are very close together, or they can have bumps that are very far apart, like this, see? And the different distances between the bumps determines how much energy the waves have. And we could get into a whole discussion about that, but a particular size of wave is called heat. So there is an electromagnetic wave called heat. There's also electromagnetic waves that make the visible light that we see. In fact, if I do it really fast here, the longest waves are what we call radio waves. These are the longest ripples in the electromagnetic field. And then if they get a little bit shorter, now I can't do it to scale. Just to give you an idea of scale, the distance between the bumps on these could be as much as 1 kilometer or more. Big, huge, rolling waves. And then on this next picture, this is like 1 centimeter. So obviously it's too hard to draw that to scale. So I just draw it like this, but these would actually be waves that the bumps were more like this far apart, right? Which is quite a bit smaller. But if you drew that to scale, then when we got to the end, we wouldn't be able to see any of the other waves. So right here is another wave that's shorter. These would be even shorter. These waves would be probably almost too short for me to draw. They would be so tight together that it would be almost like a straight line. You wouldn't even be able to see them. These are the waves, what we call I didn't label this one. These are microwaves, just like in your oven, the second one. And this one are the infrared, which means just below red. And that's because the next waves that get a little smaller is the red, and then there's orange and yellow, all the colors of the spectrum. Orange, yellow, green, blue, and violet. And these get progressively smaller. Violet is, see how I'm trying to make them very quickly smaller as we go. But then you can get ultraviolet waves. Ultraviolet waves, which are even smaller. Then you can get something called X-rays, which are really small wiggles. And then you can get something called gamma rays. These are very small, small, small wiggles. These wiggles up here on this end are so small. They're very highly energetic. These things can rip your cells apart and rip molecules apart. So they're very dangerous. And they do come out of the sun, for instance, makes all these things. Because the sun is a nuclear explosion. And in a nuclear explosion, you're wiggling a lot of charged particles, making all these different waves. These are called the visible light waves. To get an idea of the wiggles, okay, if you were to measure between the bumps, you're actually talking about something called nanometers, billionths of a meter. So this would be, red would be about 700 nanometers, which is about 7, and then 1, 2, 3, 4, 6, about that many. Actually, the other way around, sorry, that's not right. It's 0. They're very small. 1, 2, 3, 4. About that far. That's how many meters it is between the bumps, right? Well, there's a millimeter right there. And this is a a millimeter cut into 1,000 pieces. So you see these are very tiny waves, very, very small. That's the red right here. So you can see why the scale can't be drawn on the board. However, we're interested in this guy right here, this infrared section. These waves in this section are actually waves that can wiggle molecules and create heat. So remember we talked about how the molecules of something get wiggled? Well, there's a couple of ways they can wiggle, but one of the ways is just like if you go to the wave pool and you're sitting here, waiting with your little floaty on, and then a big wave comes along, well, what happens is you ride the wave. You go up and you go down and you start to wiggle. Well, just like that, an infrared wave can come along and take a molecule or an atom or anything, essentially, and make it go up and down and wiggle. And of course, if it makes it wiggle, remember, wiggling makes it hotter. It has more energy now. It's been given kinetic energy by the wiggly wave to make it wiggle. And that's why it's hotter. It has more kinetic energy. It's all just a matter of how much kinetic energy you have. So these waves are all around us. And these waves, when they travel, are called radiation. Now, some of us think radiation is bad, and it is bad if you look at these guys up here that can damage your molecules. But light is also radiation, and it's not bad. It doesn't really hurt us. We use it to see. Microwaves are radiation. Even the radio you listen to, when you tune into a station on the radio, it's traveling through the air as radiation. And of course, heat is a form of radiation. And so the wiggling of waves traveling through the electromagnetic field, okay, infrared waves traveling through the electromagnetic field are a form of heat. Electromagnetic field. In fact, radiation is any waves, but when we talk about heat, let's add heat here. Heat radiation is infrared waves traveling through the electromagnetic field. So this, of course, is how heat can get from one place to another. And that's what we're going to look at next, how heat travels, right? So one of the ways is obviously by wiggling its way through the electromagnetic field, and we call that radiation. So that's one way that heat can travel from one place to another. So, you know, if you had a pond, you put a cork over here, and you put a cork over here, and it's calm. So you poke this with your finger, you make it go wiggly up and down, and it starts to make a wave. Well, now the wave will travel. It will bring the energy, the movement of this cork over here, and once it hits the other cork, this cork will all of a sudden start to wiggle too. So you've transferred the wiggle. Even though you never touched this cork with your finger, you created movement here, and that creates kinetic energy, which was transmitted through the water ripples to the other cork, which now has kinetic energy. So you've moved the energy from one place to another. That's the movement of heat, if we apply this analogy to the electromagnetic waves in the infrared range. That's how heat moves, and that's what we mean by radiation. Now there's two other ways, in fact, that heat can move around. I'm going to get off the red because it's hurting my eyes. The second way that heat can get around is by something called conduction. Now radiation happens everywhere. It happens in the electromagnetic field, right, which does not depend on matter. The electromagnetic field is not made of matter. That's why heat can travel through space. We can feel the warmth of the sun, right? I don't know if you've ever thought about this, but there's the sun. It's a big ball of giant nuclear explosion. It's not really fire. It's not actually burning like fire. It's even hotter than fire. And it's a nuclear reaction giving off tremendous amounts of heat that wiggle towards us as waves in the electromagnetic field. And here we are on the Earth, and we can feel that heat. You can go outside in the summer and feel the warmth of the sun on your skin. And what's cool, I think, is that is 150 million kilometers away. Imagine having a bonfire and you were standing, even if you stood 40 feet away, you wouldn't feel the heat. But the sun is so powerfully hot that you can stand 150 million kilometers away and you can still feel the warmth coming towards you. And of course, that warmth is coming through space, which has very little or no matter. So that must be traveling through the electromagnetic field, not through matter. Conduction is more traveling through matter. And it's pretty easy to understand. If we take a metal bar and let's put our little flame here again underneath it, light it on fire. So the little particles here are getting energy from the flame. Okay? The energy from the flame, the heat, is causing them to jiggle more. So they're starting to jiggle back and forth and vibrate. Well, imagine what happens if you're in a crowd of people and you start jiggling all around, right? You're going to bump into people next to you. And so what happens is when this little molecule here, or atom of metal, absorbs the heat energy, it begins to wiggle. And when it wiggles, it runs over here and it bumps into this other guy and causes him to wiggle. And then he bumps this one and causes him to wiggle. And so this transferring of the wiggling by bumping directly into each other makes the wiggling, which is the heat. Remember, the heat isn't the particle, the heat is the wiggling. You just keep banging around and passing that wiggle. Pretty soon, way down here, all these molecules are wiggling because they've been disturbed by bumping one to the other. So over here, we start to feel the bar getting hot, even though the flame is way over on the other end. And so what's happened here is the jiggling molecules have passed their heat or their jiggle along by bumping into each other or interacting with each other, bumping. So that's called conduction. When matter particles sort of transfer their heat by interacting directly with each other and passing their wiggles on. Conduction. So we say if you're a good conductor, that means that your molecules are held together in such a way that they can easily pass on wiggles from one to the other. Some molecules are held more securely by their bonds in their structures, right? Styrofoam, for instance. The particles don't wiggle as easily, so it's hard to get heat. If this was a piece of styrofoam, these would wiggle and they would bump nearby, but these guys would be like, I don't want to wiggle, and they wouldn't wiggle much, and pretty soon the wiggle would die out and the heat wouldn't travel very far. So that's why we call styrofoam an insulator, right? It doesn't let the heat travel. And that's because of its molecular structure. It's the way it's built inside and the way its atoms are being, its molecules are holding each other together. But some things like metals, the atoms are much freer. So when they bump all the way down, and they can bump and spread the heat very quickly. If you put a hot metal, a piece of iron in a fire, very soon, even if you're holding it over here on this end, like here, it still gets very hot because it's a good conductor of heat. So conductors of heat are transferring heat by conduction. There's a third way that heat can travel from one place to another, and that's called convection. And this also involves matter. Primarily, it involves liquids and gases. Which we call fluids, right, in physics. Sometimes we think of fluids only as liquids, but gases are fluids too. So all these things their molecules are not held together as tightly as in solids, and so they can move. So here's what happens in convection. And here's a good example of convection is what happens on Earth when the sun shines. So here's the ground, right? So the sun is shining over here, and it's sending those electromagnetic ripples. Okay, we don't see them, but they're there. It's sending them through. All right, I'm just going to double check. I think I lost my... Okay, sorry, I had a little sound problem. I think I got it back. So let's look at these ripples. Let me get some red here. Okay, so these little ripples are coming like this. These are infrared electromagnetic waves. So this is radiation from the sun. Now radiation just usually goes right through the air. It doesn't really interact much with the air. But when it hits the ground, these solid atoms begin to jiggle. So the atoms of the ground now are riding these waves, and they are starting to jiggle quite a bit, which means the ground is warming up like hot pavement in the summer day. Well, some of these molecules are going to wiggle up and down, and they're going to bump into the air molecules. And they're going to make the air molecules wiggle. So that's conduction, right? They've bumped into the other molecules. So that's conduction happening at this part. And then what happens is when these molecules of air begin to wiggle, they take up more space. Just like that person, if you go to a dance, there's always a couple people who like to jump around wildly. And what happens is the crowd kind of backs off and gives them room, right? Because you don't want to bump into them. So what happens down here, let me just erase that circle. What happens where all these particles are jiggling is that they increase their space, which means the density changes. Density is lowered because of all the jiggling. More space between the particles means it's less dense. Now, less dense air, right? It's also warmer air, isn't it? Because of all the extra jiggling. So what we have here is warmer, less dense air. Well, if it's less dense, the air up on top, which is not jiggling as much, is more dense. And so more dense means it will sink. It will tend to sink down, and the less dense, warmer air will tend to push up and rise above it. And so what that creates is it creates a huge sort of current where the warming air, actually, let me do that differently. The warming air is sort of pushing up here in the middle. So this is the warmer air because it's less dense. And around the outside, we have cooler air from the top, sort of coming down to fill in the spot, right, where the air was leaving. It's like it's replacing the warm air that rose up from that spot. But as the warmer air goes up higher, away from the ground, there's less bumping with those ground molecules, and it begins to cool off. So the warmer air turns to cooler air, and then it creates sort of a cycle, right? The air starts to go around like this, around and around, down here and up here. And the same happens here. It goes down and around, and it creates these sort of weird donut-shaped currents of air. And so what that means is, if you had warm air here, it rises up and it moves to the top. Now it cools off as it goes, but you're still transferring the warm heat. So convection is kind of like heat that's riding along with molecules that are moving from one place to another because of a change in their density. And that's why this usually only happens in liquids and in liquids and gases, because those molecules are less rigidly held together and they can move past each other more easily. So this is called convection. This is called a convection current. And in fact, we're talking about the ground and the sun. This is what makes weather. Convection currents make weather. Because another thing that happens is as warm air rises, warm air can also hold more water. So rising warm air here in the middle, right here, as it goes up and cools off a little bit, the water condenses and it makes clouds. This is where you would find clouds, wherever there is warm air rising up. And then the cool air comes around the outside and fills in the hole. And then, of course, if you're standing here on the ground, you feel the air blowing by. That's what creates wind. So these convection currents make the wind. The wind is air that's moving because the density of the air is being changed, and somewhere nearby, warm air is rising and cool air is sinking. That's a convection current, and it's moving the heat from down low near the ground up higher. So it's another way of heat being moved. All right? So convection is huge for things like the weather. It is basically the driving force behind our weather. But it's also found in other smaller things. If you ever see a pot of boiling water, when it gets hot, right, you'll notice that there are sort of like bubbles, boom, 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 rolling bubbles on top. Well, that's because inside the pot, there's rising hot water, which rises up and it bubbles over and then it sinks back down. And so it makes these little currents inside the pot that go up and go back down. If you're really, really observant, if you look at a very hot cup of coffee, just as hot as you can boil it, you can actually see, just by it sitting there, you'll be able to see little spots on top where the water seems to be pushing a little bit higher. You can actually see that if it's super, super hot. It has to be very hot coffee, and it has to be very still. So by the time it gets still, it often cools off so much that you can't see that. But I've seen it myself, and you can see on the surface of a hot, hot, hot cup of coffee that's not disturbed, you can see these little bulges from these convection currents. So that's it. So heat is kinetic energy of matter, jiggling of particles, right? And that jiggling of particles is because of the vibrations or the jiggles in the electromagnetic field. That's actually the real source of heat, magnetic field. Because in order for you to jiggle, something has to make you jiggle. So it's like we're in a big, giant, invisible ocean that's actually a wave pool. And as the ripples come along, things ride these waves and they jiggle up and down. So it's the vibrations of the electromagnetic field, and in particularly in the range of infrared, that make things wiggle. The other ranges, the microwaves, the gamma rays and things, those wiggles do different things. They create changes in the molecular structure sometimes, or it's slightly different. So it's typically the infrared region that is responsible for most of the heat energy, the vibration of the molecules. And there's three ways that this heat can travel. One is radiation, which is the movement or the wiggling of the electromagnetic waves as they travel from one place to another. Think about the corks bobbing in the water. You push one cork, and you can make another cork 30 feet away start to bob because the waves traveled to it and made it jump up and down, gave it kinetic energy. The other thing is conduction can transfer heat, because conduction is when one wiggling molecule bumps into its neighbor and causes him to wiggle and sets off sort of a chain reaction of bumping and wiggling that moves through a cloud of molecules. And then we have convection, which is the changes in density because of the fact that you're wiggling bigger, wiggling more vigorously, that creates more space. And typically this is because this is in fluids that have molecular structures that allow the molecules to move more freely. And you get changes in density. More wiggling means less dense, and less dense and more dense because of basically gravity. Right? More dense things tend to fall down lower. And so the cool, more dense sinks, cool, dense sinks towards the ground, and warmer, less dense rises. And you create these currents of air where the warm air goes up and the cool air comes around, and you get this current or this giant moving, it's wind essentially, is what it is. It's a wind. And that's a third way that heat can travel from one place to another. And there you have it. That's the intro to heat.